Bum 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 bum. Chocolate milk. Ba-da-da-da-da. Okay, so we're looking at Kepler's second law of planetary motion, and we're going to look at some ellipses here. And in talking about the ellipse in general, we'll cover Kepler's second law here. So the first thing to note is that the planets in general are not moving in perfectly circular orbits. In our own solar system, a planet such as the Earth is moving in a nearly circular orbit, but it is not in a perfectly circular orbit. It's a little bit off. And if a planet is a little bit off in a circular approach, then that kind of more oval shape, even if the oval shape is only slightly oval, like that's a pretty good circle, but it's not perfect. That's an ellipse. So these ellipses, while they're not super elongated like this, they're really pretty circular in our own solar system. They're not perfect circles, and thus they are ellipses. In talking about ellipses, there's two things we need to keep in mind. Ellipses have two foci rather. Why did I say it like that? It's so dumb. Foci. One is traditionally just about where the star is. So here is our star, the sun. And the other one is a point symmetrically on the other side of the ellipse. So these 2 points are foci. Okay. Now, there's two axes we think about on an ellipse. One is known as the major axis. It cuts across the longest part of the ellipse. So, whoops. So there's the major axis. And then we have the minor axis. And the minor axis goes across the most narrow part of the ellipse. Now, what we have and what we traditionally use in the world of astronomy and physics is a semi-major axis and the semi-minor axis. Because for the semi-major and semi-minor, we only care about the half of the major axis right here. That is the semi-major axis. And our semi-minor axis is just half of the minor axis here. And we designate that with the letter B. So there's your semi-major axis, there's your semi-minor axis. If you have those two things, you technically know a bunch of information about your ellipse. So kind of a neat thing there. Now, when we're talking about an object moving around the ellipse, let's say here is a little planet moving around the sun in this kind of terrible orbit. Maybe it's a comet, right? A very common comet that everybody knows about is Halley's Comet, orbital period of about 76 years. And as this comet is coming around in this ellipse here, when it gets right here, it is moving tangentially. Its velocity is moving tangentially this way, so its velocity is moving like that. And it is moving fastest right here. Okay? We're kind of falling into or near the star, and as we fall, boom, we slingshot around the star right here. This distance from the closest approach to that foci, or our star in this case, this is what we refer to as a perihelion. We are at the closest approach. So this is a perihelion. And para being close, helion being Helios, our sun. But if you had like a planet, like a moon going around a planet, or maybe a satellite planet, we'd use like a G, like para-G, G being Gaia, and Earth. But we are moving the fastest there. As our comet or planet or whatever is orbiting this body, kind of falls away, we're kind of being like thrown up away from the sun. So we're starting to slow down as we come out here. And when we get to this very far away point, we're still moving tangentially at each point. But out here, we are moving the slowest. Okay? And if we take this entire distance here, we call this, well, over here, this is the perihelion, we call that RP. Over here, this is our aphelion, or aphelios, and we designate that with an RP. So that is that full distance from here all the way out. Okay? And that is our slowest position. Here, we're just kind of like reaching the top of a throw, and we're turning over, and we're going to fall back down and speed up. Okay? Now, in terms of the eccentricity and how like elongated this orbit is, there are a few things that we can kind of think about for it. We only need to know A and B, because if you have A and B, the semi-major and semi-minor axis, that tells you, how far over and how far up you are, which allows you to make this curve, and due to symmetry, you can make the curve everywhere else. So the eccentricity can actually be thought of in a few ways. If you have a perfect eccentricity, then your eccentricity is 0, and you are a perfect circle, mathematically speaking. If you are in an ellipse, you're a non-perfect circle, then we could say your eccentricity is equal to the root of 1 minus b squared over a squared. And since b is smaller than a, this is going to be like 1 minus some value here. And it gives us a value at least that is less than 1. It has to be a value less than 1 here. Okay. This is an ellipse. If you have a value of exactly 1 for your eccentricity, then you've what's created a parabola. And you don't have an actual orbit here. If this is your foci or one of them, you're gonna kind of just come in and go out and never come back. Okay, you're gone. And if you actually create something where you're kind of coming in and you're going out like that, then you don't have just a parabola, you have hyperbola, which is 1 plus b squared over a squared. And this is a value greater than 1. Okay, so those are ways that we can think about ellipse, and all you need to know is the semi-major and semi-minor axis. Now, if you know you have an ellipse, then we can think about these in other ways. We can say the eccentricity of an ellipse can be thought of as RP over RA, where your perihelion is the closest approach and your aphelion is your farthest approach. So this is some non-zero number, but it's also smaller than 1, so it's not a parabola. You can also think about this as, and this is a kind of like weird thing of thinking about this, so you can think about this equation just solving for the eccentricity like that. But if you know the eccentricity, but you don't know how far away your closest and furthest approaches are, you can also say this is equal to 1 times 1 minus e over 1 plus e, where this a is your semi-major axis. And what that allows you to do is it allows you to equate these equations together. So if you don't know anything about your semi-major axis, but you know eccentricity, you know your r values, then you can find it. But if you don't know an r value, then you can, but you know the semi-major values, then you can use this to go find that. These equations here, they just kind of go together. There's technically 2 of them there, but you can kind of mix and match them to figure out a whole bunch of things regarding your orbit. Some other things we have, if you want to know your velocity at perihelion, perigee, aphelion, apogee, then we can actually use a conservation of angular momentum to do this. There's a whole extra video out there on that, so go check out that video. But in short, what we see is the velocity at perigee is just going to equal the distance to apogee multiplied by the velocity of apogee over the radius to perigee. And then the velocity at apogee follows a very similar equation where it's the radius of perigee, velocity of perigee over the radius of apogee, okay? And that's just the conservation of angular momentum there. Like I said, there's a whole other video about it if you want to check that out. One equation that isn't really talked about in high school physics courses, but is huge in the world of astronomy, is something known as the Vis Viva Equation. For the Vis Viva Equation, it's really a conservation of energy equation, but what it allows you to do is, if you know the semi-major axis and the mass of the system that you're orbiting around, then what you can say is that the velocity at any point in the orbit is equal to the square root of gm times the quantity of 2 over r minus 1 over a, where this r right here is your current position, like how far radially are you from the foci that you're orbiting. This gives you the velocity at any point in the orbit, which is a kind of cool thing. It's a conservation of energy approach. You see it a lot in astronomy. It's used a ton there. But in the high school physics class, we really don't use it. But I thought I'd show that to you just as a little bit of a extra win there. So this is an ellipse, and it's what we do and what we use all the time. Here's how we describe them, what we're talking about. So if you see these A's and B's for semi-major and semi-minor axes, that's what we're talking about. And we're just talking about how non-circular something is. So nothing too much there, but a kind of neat thing for you to take a look at and take a think at. So with that, adios. Take it easy.